The arrow of time expresses the fact that in the world about us, the past is distinctly different from the future. Milk spills but doesn't unspill. Eggs splatter but do not unsplatter. Waves break but do not unbreak. We always grow older but never younger. These processes all move in one direction in time, and they are called the time irreversible and define the arrow of time. Now, what is the puzzle? The puzzle is this, that there are gazillion processes in the world taking place in one temporal order.
Oh yeah.
They unfold in one temporal direction and we never see the reverse of those processes. But why so? Does it mean that the laws of physics allow the paths of flowers to blow in the wind, but they simply do not allow the reverse process to take place? But this is not true because reverse processes can be easily explained by the laws of physics. So imagine you have a football and it is hit from the home and it soars into, say, the outfield. And let us say the trajectory of that ball is x of t.
So this is the trajectory of the ball from the home, that is t is equals to 0, to the outfield, that is t is equals to 1. And it is called like x of t. So the equations of motion can be written like fg is equals to mg or m into t square x upon dt square. So if we consider the reverse trajectory, the reverse process, so this is like the ball starting from the outfield and coming to the home, and say this is known as x bar t. Simply x bar t represents here x of 1 minus t, as we put x bar t 0 at t is equals to 0, so it is equals to x of 1, means x bar 0 here is equals to x of 1, that is initially seen in the first figure. And if we consider x bar of 1, that is simply x of 0. So this is x bar of 1 and it is equals to x of 0. So simply the ball is coming from x bar 0, that is the initial position at t is equals to 0, to x bar 1. Now finding the derivative for x bar, dx bar upon dt can be simply written as dx1 minus t, since x bar is a function x1 minus t upon me dt, and here 1 minus t is acting just like a dummy variable, and simply just multiply and divide it by 1 minus t, or you can say that I have applied a chain rule here, that is dx 1 minus t, derivative of this term first with respect to 1 minus t, then derivative of 1 minus t upon dt. This is minus 1, as with respect to dt, if it is differentiated, 1 acts like a constant and minus t derivative is minus 1. Here simply we can write that 1 minus t is a dummy term, so it can be just simply replaced by t over here, and it represents the differentiative of the argument x. So this is dx upon dt, that too with a minus sign, which is dx bar upon dt. So simply states that the velocity of this trajectory would be the negative of the velocity of the initial trajectory. Now taking the double derivative of this term, d square x bar upon dt square is d square x upon dt square. So it proves that if the trajectory from the home to the outfield follows the laws of motion, so does the reverse one also.
So the point here is the reverse things can happen, but we do not see them happening is just due to the fact that they are very, very unlikely to happen. This is where the concept of entropy pops in. Entropy is a measure of randomness or disorder in a system. Now, the point is that how to measure it. It is given by the Boltzmann formula of entropy. S is equals to K ln omega, where K is the Boltzmann constant and W is the number of microstates, or in simple words, omega can be understood like the number of arrangements a system can have to leave it unchanged as before. For example, kids running in a classroom may change their position several times, but they still are in a state of randomness and disorder. So there are many possible ways in which they seem to us like in a very disordered manner and running here and there. On the other hand, if we make the students sit in a particular fashion according to the serial number, then the possible number of arrangements are very few. It is considered to be an ordered system, and an ordered system has a limited number of rearrangements which can be done to look at the same as before. It means that the disordered system has more number of arrangements to make it see like before than the ordered one. And from the formula of entropy, S is equals to K ln omega, the number of rearrangements of a system to remain that system to be unchanged is directly proportional to the entropy. It means the more number of arrangements is equals to more disordered system is equals to more entropy, and the less number of arrangements is equals to ordered system is equals to less entropy. It is a tendency of nature to set itself in a free state or disordered state than the ordered state, because there are many number of arrangements possible for the disordered system. We comb our hair daily, but till the evening they get fully messed up, and they are the few examples which illustrate that it is a tendency of nature to move from less ordered state to disordered state, but not from disordered to ordered state. Or in other words, we can say that we always see the system moving from less entropy to high entropy, but not the vice versa. But have we fully answered the question? Not really. You still want to ask yourself, if the high entropy states are more likely ones, why do we ever see any order at all? Why do we have a pristine wine glass? Where did this order come from?